That provision we have kept.
So we can, I think we can start now.
We can start.
Yeah.
Okay, so ladies and gentlemen, esteemed guests and experts from all around the world, welcome to the international webinar on the Carrington effect and its impact on regional grids. So this event is jointly hosted by the International Solar Innovation Council, or InSIC in short, and the International Solar Alliance, ISA. Today's webinar is a pivotal step in understanding and mitigating the effects of Carrington storms on our regional power grids. I am Richik Ghosh Thakur, a board member of InSIC, and I will be moderating this event. We are privileged to welcome distinguished experts from prestigious organized institutions like NASA, the Finnish Meteorological Institute, FMI, Helsinki University, and the European Space Agency. Their invaluable insights will illuminate the potential implications of Carrington events and enhance our collective efforts in building resilient grid systems. This webinar aligns with the One Sun, One World and One Grid initiative of Government of India, underscoring the importance of international collaboration in tackling shared challenges in renewable energy. Together, let's explore this crucial topic, enhancing our awareness and developing effective strategies for risk mitigation. Thank you for joining us in this journey towards a more sustainable and secure energy future. So let's proceed with the program now. It's my pleasure to introduce Professor S.P. Gonchoudhary, a leading international figure in renewable energy and the founder of InSIC. He'll deliver the welcome address. Professor Gonchoudhary is acclaimed for his innovative work in solar photovoltaics and rural electrification. A recipient of numerous prestigious awards, including the Green Oscar, Mission Innovation Champion Award, National Science Academy Award, and other awards. His contributions have significantly advanced renewable energy, benefiting millions globally. He was also the Special Secretary of Energy in the government of West Bengal. So please join me in warmly welcoming Professor Gonchoudhary. Over to you, sir.
Okay, thank you, Richie. Thank you very much. Dr. Ajay Mathur, Director General ISA, who is likely to join. Mr. S.R. Narasimhan, the Chairman and Managing Director, Grid India. Dr. Meena, Professor, Department of Physics, University of Helsinki, and the Director of the European Carrington Project. Dr. Antti, the Director, Heliophysics Science Division, NASA. Esteemed guests, colleagues, and friends from around the world, I extend a warm welcome to all of you. Good morning to our friends from the United States. Good afternoon to those joining us from Europe and Africa. And good evening to our participants from India. We have gathered today for an important webinar on a critical issue that has far-reaching implications for our global power grids, the potential impact of Carrington events. These solar storms have the capacity to cause devastating consequences, leading to widespread and long-lasting damage to our extremely high-voltage transformers. The threat posed by such an event is very real, and it is imperative that we take proactive steps to prepare and mitigate the risks. The webinar aims to explore the need for a Carrington protocol, a set of clear guidelines for power grid operators to protect these vital transformers during a solar storm. While implementing such measures may necessitate temporary blackouts, it is a prudent and necessary step to prevent the far more severe and prolonged grid failure that could result from inaction. We are incredibly fortunate to have with us today representatives from Finland, a globally recognized leader in Carrington storm research. Their expertise, coupled with the invaluable insights from scientists at NASA and ESA, will be instrumental in guiding our discussions on how to address this global challenge effectively. We'll be exploring the vulnerability of countries like India and China to such events and the potential for India's once. This webinar is a joint initiative organized by the International Solar Innovation Council, we call shortly InSIC, an international organization dedicated to promoting innovation in the solar energy sector in collaboration with the International Solar Alliance, which is known worldwide now. It represents the first in a series of expert-led closed groups webinars, bringing together the collective knowledge and experience of Finnish space weather scientists and other distinguished guests. Our goal is to work together to develop a comprehensive plan that safeguards our critical infrastructure and protects billions of people from the potential disruption caused by a Carrington event. By leveraging the expertise and insights of our esteemed participants, including representatives from the West, East and South African power pools, Grid India and the Power Grid Corporation of India, and many other distinguished guests and experts, we can forge a path towards a more resilient and secure global power grid. Once again, I extend a heartfelt welcome to all of you, and I look forward to a productive and insightful discussion as we tackle this pressing challenge together. Thank you for joining with us today in this very, very important webinar. Thank you very much.
Thank you, Professor, for welcoming all our guests, all our invited speakers and the participants who are basically experts and professionals in the power grid sector. So I'll move on. So we have a little bit change in our schedule. So now I'll invite, it's an honor actually to invite Mr. S.R. Narasimhan, the Chairman and Managing Director of Grid Controller of India Limited, Grid India we call in short, for the inaugural address and the special address. With an illustrious career that began in 1986, Mr. Narasimhan has been a pivotal figure in India's power sector, contributing significantly to power system operations and electricity market reforms. He is a respected member of several professional bodies, including IEEE and SIGRE, and the recipient of many prestigious awards for his outstanding work. His vast experience and expertise are invaluable to our discussions today. So Mr. Narasimhan will be delivering the inaugural address as well as the special address. Welcome, sir, and over to you, sir.
Thank you. Thank you, Richik, for the introduction. And good morning, good afternoon, good evening to all the participants, depending on which part of the globe you're from. It's basically an astronomical phenomena that we are not all at the same time. You know, at the outset, let me thank the organizers, the International Solar Innovation Council and the International Solar Alliance for having me on as a speaker in this illustrious galaxy of speakers that we have today. You know, and when Dr. Chaudhary reached out to me last month, you know, mentioning about this topic on Carrington effect and all, and so my immediate reaction was that at least the Indian grid, you know, by virtue of our location being closer to the equator, you know, so geomagnetic disturbance, we actually don't have any incident to recall, you know, from our archives or, you know, going forward. That's possibly because of the locational advantage we have. So Dr. Chaudhary assured me that there would be different set of speakers on the Carrington effect, especially specifically, and he needs me mainly to delve on, you know, the challenges that we face in ensuring reliability of the grids. So thank you for having me as a speaker. And most of you would be aware that the Indian electricity grid, it's the largest national synchronous grid in the world. And if we talk about synchronous systems, it's the fourth largest synchronous system in the world, and ensuring reliability of this large grid, that's something which it's a challenge, and more so as we are navigating this energy transition, and the challenges are only getting more and more, complex, and you have more, I would say, unknowns. And it's events like this, where we try to gradually try to understand events, which would be a rare event. But yes, we prepare ourselves to handle these challenges. And so that's the advantage of having events such as this. And then when after Dr. Chaudhary spoke to me, I realized that as a system operator, we handle so many challenges. Each day is different. When you come to the workplace, you wouldn't expect what uncertainty would be there. It could be anything. And traditionally, it has been either extreme temperatures. In 22, we saw in April 22, a 1 in 122 year summer weather phenomena, extreme temperatures throughout the country, and that traditionally it leads to a very high electricity demand, and the resource adequacy becomes a serious issue. So that's a challenge which operators worldwide face. And in 2023, we had a similar event, like August and September. It was a 1 in 122 year phenomena again, in terms of record temperatures, the minimum amounts of rainfall in 122 years. So our demand surpassed 240 gigawatt. It was an all-time high. We were actually forecasting something like 220, 225 gigawatt range. And this failure of the monsoon, it led to a spike in demand. And if you look at the irony, the contrast, just in the month of July, the northern region had heavy rainfalls, in Himachal Pradesh and all these hilly areas. There was heavy rainfall, and across 6 river basins, we had to actually close down all the hydro because of increase in silt level. There was a 10 gigawatt outage of, this was something which I've never experienced in my more than 30 years career in power systems. So these are exceptional events, and for at least 4-5 days, we lost about 10 gigawatt of hydro because we couldn't operate them because of the high silt levels on account of the very heavy rainfall in the upper reaches of the Himalayas. So that's one extreme. So, and then in August, we had a monsoon failure. Unfortunately, the 15 days of heavy rainfall in northern region, we could at least fill up our reservoirs in northern region. That was a blessing. So that is one aspect. Natural calamities such as earthquakes, floods, and cyclones, we deal with it every year in the month of around October, November. We have one part of the country affected by tropical cyclones, the Odisha and West Bengal coast. So that's another event for which we prepare ourselves, and the post damage to the equipment, there are some outages which take sometimes days, or a few cases it could even be months to recover, and so that's the kind of challenge, which we face. And earthquake, again, it's an instantaneous thing. You cannot forecast, and we end up many transformers, they go out because of the Bhopal's relay operation, and you have a sudden disconnection of load. So the moment frequency goes high because of loss of load in a pocket, and we find out that yes, there's actually been an earthquake in that area, which has led to disruptions in the distribution system. So we handle all these. And now with energy transition and digitalization, there are a whole set of new uncertainties. I spoke about failure of monsoons, but with wind and solar getting added, we would have periods of wind and solar drought also. We had in like January 24 was an exceptional month where, despite addition of solar capacity in 1 year, the solar generation was actually much, much lower than what it was in January 23, because there was a countrywide, there was a cloud cover and fog over many parts of the country, and so that has an impact on how we operate our system, in terms of conventional generation. Then behavior of inverter-based resources, that's another aspect, worldwide, how these inverter-based resources react to a fault in the transmission system. That's an area of concern. There's a report that we brought out in November 23 that's available on our website, so that those interested could take a look at that, how we have mitigated those trippings, through several measures related to standards, equipment standards. And cyber security is another new unknown, and that's also we are taking steps to mitigate this. We have a cyber crisis management plan, and we try mock drills. So the other one, and other extreme, some of it could also be man-made. On 3rd April 2020, our Honorable Prime Minister, he announced, it was the pandemic phase, and then he made an announcement that on 5th April, 9 p.m., 9 minutes, let people switch off their lights as a mark of solidarity to all the healthcare workers, And we had 36 hours in which we had to plan the entire, like how would the system behave? What would be the load loss? We forecasted 16 gigawatt reduction in demand, but it actually turned out to be 32 gigawatt because generally there are so many messages in the social media, that some people, they switched off all the appliances in their residence. So it was actually 31 gigawatt reduction over a period of 20 minutes, fortunately. I shudder to think what would have been the situation if at exactly 9 p.m. people switched off, So some diversity we had, we could. The report is available on our website on that particular event also. They've given out all the data. So the resilience of the power system, that the point I'm trying to make is the resilience of the power system has acquired an entirely new meaning with so many uncertainties that we face. And even some of the events, they generally fall in the category of low probability, high impact events, And there, what's important is that in all these events, what is the reaction time available to the operator? Is it a problem of only stability in real time, whether you're talking about transient stability and midterm stability? Or is it a problem of long-term stability, that you have a lot of outages after that event, which disrupt your operations in the long term? So which category it lies, the reaction time available, that's important. So for instance, if you look at astronomical phenomena, solar eclipse is a very common event, and I think while the entire US and Europe, they are preparing themselves for the 8th April 24. In India, we had 2 annular eclipses, December 2019 and June 2020. So fortunately, the solar quantum was much less, 6.5 gigawatt reduction we had in December 2019 and 11 gigawatt in June 2020. So we could control that with our hydro and gas resources. But one could very well imagine that 2030 and beyond, when we would have 300 to 400 gigawatt of solar, and if there is a solar eclipse, how are we going to gear up for that? And I just looked at the data and I found that yes, 27 there would be a partial eclipse, 31 there would be an annular eclipse, 2034 March 2034 we would have a total solar eclipse. I looked at the trajectory. Fortunately, it's just touching the northern part of our country, the Jammu and Kashmir area. So we would try to work out, like with 400 gigawatt of solar generation, how would we handle that situation? And that's where, the demand response and other things would come in, when we would have a reduction in solar generation. So 2034 is still way off, but we'll have to prepare. So eclipse is a planned event. You know everything. All the data is there. One could very well work out. The problem is less severe if it is a cloudy day. It's more severe if it's a clear day where you have more loss. So that's one aspect. And now this Carrington effect is something, which it's a different category of event, in the sense that you need to operate at a lower load generation balance. Once you have evidence of the storm impacting, then many loads would have to be switched off, transformers would have to be switched off. And so operating at a low load generation balance is something that we do whenever we have a thunderstorm, dust storm event. But then this is a sudden event. I think not more than 1.5 hours notice one would have for a solar storm event. And so it's going to be a challenge. And at least from the Indian grid side, we would love to learn from our experts elsewhere who would be there on this panel and try to take steps to mitigate, like tomorrow, if we were to have such an event, then how would we mitigate? The more serious problem is that already there's a supply chain constraint. If you're looking at new assets which are getting added to the grid, there's already a supply chain constraints for transformers and other high voltage DC equipment. So if a Carrington event were to impact the existing equipment, then it would place much more stress on the supply chain, and that's something which we all need to be prepared for. And apart from this, the impact on GPS, the time synchronization, that would also have an impact on the monitoring of phasor measurement units, which we have in our control centers. So that's something which we need to look, and the behavior of inverter-based resources and the power electronic devices, how the control systems would behave in case. So these are the unknowns, and I would love to hear from the experts in today's panel. I stop here. Thank you so much for having me as a panelist in today's discussion. Thank you.
Thank you, sir, for your valuable insights. So this is important because India is now able to handle, India's power grid is resilient, and we can handle several contingency events also, as sir pointed out, Narasimhan sir. And this Carrington event, what dangers does it have in our system? So that has to be investigated. So several sensor systems, as Mr. Narasimhan mentioned, that PMUs and some other sensor systems will get affected. How will they get affected? This needs to be investigated. So again, sir, thank you for your valuable insights. And now I would welcome Mr. Disto, who is the Vice Chairperson of InSIC, to introduce our keynote speakers.
Yeah, I have the great honor of introducing our keynote speakers. Dr. Antti Pulkkinen is the director of the Heliostatic Research Division of NASA in the Goddard Space Flight Center. The Goddard Space Flight Center is the institute that developed the technologies that brought the first humans to moon and space probes to the outer planets of our solar system. We could say that Dr. Pulkkinen is, among some other things, the director of NASA's Space Weather Research Program. But he is also considered the father of the Carrington legislation in the United States. He was instrumental in pushing through a law that made it obligatory for the power grid operators in the United States to prepare for extreme space weather events. And this actually made United States the first country in the world who has a law related to these matters. And it's actually still the only country which has a law related to the Carrington events and to the geomagnetically induced currents. And I hope that we will be able to change that. But at the moment, this is the only law that exists in the world related to these matters. Then Professor Minna Palmroth used to be the chairwoman of the Space Advisory Board of the European Union, and she actually held that post, I think, until European Union decided to dismantle these advisory boards. She was also the director of the European Carrington project that provided the first accurate modeling of what actually happened during the original Carrington storm in 1859. And her team also produced the first assessment of the vulnerability of the Chinese power grid during extreme space weather events. Professor Palmroth has developed a modeling program called Glaciator, which is currently the best and the most accurate simulation of the space environment, near space environment of the Earth. And last year, she received the Copernicus Medal Award, which is one of the most prestigious science awards on this planet. So what comes to the extreme space weather events and their potential impacts, I do not think that we have better experts on the planet. So Dr. Pulkkinen and Professor Palmroth, we are very glad to have you with us here today. Thank you for joining our webinar. One more thing, in the program, Dr. Pulkkinen is speaking first and Professor Palmroth next, but they wanted to change places. So I think that that's what we should do. So Professor Palmroth, the floor is yours.
Thank you so much, Risto, and esteemed Professor Mathur and esteemed Chairman Narasimhan. I'm very, very glad and honored to be here today. I'm very honored for this invitation to present in your distinguished webinar, and also esteemed participants, I'm very glad to be here today. So let's see if I can now then start to I should have looked at this beforehand, because now I have to punch in my password to be able to share my presentation. Just a moment. I hope it will be okay. So if I'm now able to share. Oh, the sharing of my window seems not to be possible. So could you, from your end, start sharing the presentation?
Ma'am, what we'll do is we'll make you co-host so that you can share.
Yes,
from
yes,
your end.
yes.
Right?
Thank you very much. Yeah.
We'll do
Yeah.
that. Shanundu, can you do it? Is it possible?
Yes, yes, it is done already.
Yeah, I also sent my as a precautionary measure, I sent my presentation there beforehand. So if there would be any problems,
right. So if there's any issues, we can also present your presentation from our end.
yes,
So-
yes, that would be nice, because it seems to be impossible right now from here.
Okay.
Yes, thank you very much. Yes, so here is the first title page of the presentation. So here's who I am. I'm at the University of Helsinki and also at the Finnish Meteorological Institute. And so if you could push the next, yes, thank you. So this is the contents of the lecture. So first of all, I would like to talk a little bit about just generally what is space weather, not so much about what is causing it, but actually concentrating on the impacts that we have here on our planet. Then I will go to the what is extreme space weather, because similarly as weather systems here on Earth, we have different sizes of the weather. So we have like mild weather, and then we have extreme weather. So I will introduce what is a Carrington scale geomagnetic storm and what can it do for our planet. And then in the end, I will talk about the impacts and mitigation of this Carrington scale space weather. And I will also talk about our recent project, which was financed by the Research Council of Finland, where we actually looked at the impact on the Finnish critical infrastructure, what these kinds of space weather events could do. And if you could push the next button. Yes, thank you. And then so let's just push. Yeah. So this is now the definition for the space weather. So these are the conditions in the near Earth space which can affect technological reliability or human health. And we have very many impact types in the planet, as you can see here on the figure on the right. Satellites, aviation, power grids, rocket launches, and so on. There are actually kind of two types of causes for these space weather events. One are the eruptions of the sun, but also we have dynamics here which are made by our own magnetic field on the Earth, which are also important and also critical for our infrastructure. The solar eruption types, which are often mentioned in terms of causes for the space weather, are coronal mass ejections, which are these big loops of plasma. You can see one of that kind here on the figure on the right, this loop which extends to space. That is a coronal mass ejection where millions of tons of materia is launched into space. Then flares are smaller flashes of high energy particles, which you can also see on the solar surface on the figure on the right. Now the strength, as I already said, it varies. There are small storms statistically once per month, and then medium-sized storms maybe a few times per 11 years. I'll talk about why it is 11 years and not something else later in this talk. And then there are these megastorms or extreme storms, maybe once in 100 years. And then if you can push the next, yes. And the most important technological impacts which are caused by space weather are related to power grid, the satellite health, and signals. And as the chairman Narasimhan already mentioned, actually many of those systems that we have here on power grids are also vulnerable to the satellite signals, because we have time synchronization, which is often carried out by the satellite. So these impacts cannot kind of be thought about in isolation, but everything affects everything. Thank you. And can you put the next slide? Yes. So this is kind of now the space weather general introduction. So we have a big bar magnet inside our planet, and that extends to space. And this extension of our magnetic field into space, it interacts with the solar magnetic field. And in this interaction, space weather phenomena are born. And can you then push the next one? Thank you. And then can you just push like sequentially, I say when push again. Can you? Yes, and then one couple of two types. Yep, and one more. Thank you. Sorry about this. I should have looked at the sharing before the presentation. Okay, so here you can see the extent of the auroral zone, where actually the strongest space weather impacts occur. And normally the auroral zone is here in Finland. I don't know, you can see our Finland there underneath the red shading. And in Finnish Lapland, we can see aurora basically once per day or once per 2 days. Here on Helsinki latitudes, we can see statistically aurora once per month. The Central Europe is a few times per 10 years. And then we can see on green here, those areas which are affected by these megastorms. And here on the left, you can see this cartoon, which kind of says in one cartoon what's happening. So in the high latitudes, it's normal to have aurora and space weather impacts. And then the more towards equator you go, the more there are open questions which we don't know yet in the science community. And then let's go forward. Yep, and now I'm talking about the power grid first. And the focus here is the geomagnetically induced currents. And can you take the next one? Thank you. And let's see here first on the left, we can see the currents which are caused in the auroral zone. So here is Finland or actually the Scandinavian countries. And you can see on yellow, that is the enhancement of the ionospheric current on 100-kilometer altitude, which is caused by space weather. So this yellow now shows like the auroral zone intensifications of currents in the 100-kilometer altitude. And then can you take the next one? Then the other ingredient which you have to take into account is the ground conductivity. Here is the same area, the Scandinavian area, where we have lots of different investigations about what the conductivity of the Earth is. And you can see that it varies very much. So the red areas are very low conductivity, and then the blue areas are high conductivity. As you can see, for example, the ocean is well conducting, but then there are areas which are low conductivity. And then can you push one more? Thank you. And here then is the combination. When you have these ionospheric currents in the 100-kilometer altitude on left, and on the other hand, you have the ground conductivity, which is pictured here on the right. What it will do on ground is a thing called geoelectric field. And this is a phenomenon caused by induction of those currents in the ionosphere. And then if you can push one more time, thank you. This geoelectric field will then drive currents in all long conductors. I mean, if you have, for example, power grid here, which are depicted by these black lines in Finland, or pipelines, gas pipelines, or railways, or anything which is long and conducting, this geoelectric field will drive an extra DC current in these conductors. And then can we take the next slide? Thank you. Then I'm talking about a little bit about the satellite health, because this is also an important ingredient, especially in the time synchronization. So the next, please. Thank you. Here we have what is called the radiation environment of our planet Earth. The animation which is here on the background is showing the NASA SAMPEX measurements of very high energy electrons, which are the cause of the radiation belts. So you can see how dynamic this radiation environment is, and why is this a problem is, of course, because many of our critically important satellites, like navigation satellites and weather satellites, are embedded in these radiation belts. And can you then push one? Thank you. There are two types of radiation effects which are causing problems for satellite health. First, the Earth's own radiation belts, which you can see here on the animation, they cause aging and spacecraft charging and arcading on the satellite, both on the top of or on the surface of the satellite and in the inside of the satellite. And then the second thing are the energetic protons, which are accelerated by the sun, and they come here on the vicinity of the Earth in connection to these large superstorms, and they cause bit flips in the hardware and software. And then let's go forward. Thank you. the last thing I'm talking about is the signals, satellite signals, which are also a consequence of energetic particles in the polar cap. So the next, please. Thank you. And then let's put the next. Thank you. So here is now an illustration. If we have a satellite signal, satellite sending signal to a navigation device, which we have here on planet, for example, the mobile phones, which have navigation signals, which you can see on the right. If these signals go through changed conditions in the ionosphere, so these high energy particles, which also cause the aurora, they also change the ionospheric system, ionospheric electron content, and that deteriorates the satellite signal. So can you then push, and this occurs on an area which is poleward of the auroral zone. Here you can see on green the auroral zone where it's normally at, like typical conditions, and then on yellow you can see those that area on the globe which is affected by these signal conditions. So particles precipitate into this cone and change the signal conditions in this area. And then can you push one more time? Thank you. These extra particles in these yellow cones that are illustrated on the right, they absorb, refract, and scintillate in the area of the yellow cone, and that changes the signal amplitude, frequency, and phase. They can deteriorate satellite navigation accuracy, satellite-based timestamps, and even close polar cap aviation routes due to radio signal degradation. Also, the affected technologies are the radar signals. And then let's go forward. And then I'm talking about the Carrington storm now. So how large or how bad can things go in relation to those solar storms? And Carrington storm is named after Richard Carrington, which was an amateur astronomer in London in 1859, and he had built a device on his table where he was actually on the top right you can see the his drawing. So he had a device where he could draw the current sunspot on the solar surface, and when he was drawing the sunspot, that sunspot sent a very big flash, and this is later interpreted as the solar flare, which was launched by this sunspot on the sun. And this is the most extreme space weather event in the measured history. And solar eruption reached the Earth in 17.6 hours. Normally these eruptions come here in about 3 days, but this was extremely fast. It came only from 17 hours from, and why we know this time is we know the time when the Carrington noticed the flash on the paper, and then 17.6 hours we can see already from the measurements of that day the consequences here on Earth. These magnetic disturbances lasted about 3 days, and normally they are lasting about maybe 1 to 7 days per storm. And they included both the flare and the coronal mass ejection. And then let's go forward. Thank you. Here you can see actually a painting which is by Frederick Edwin Church, which was like inspired by the Carrington storm. And Carrington storm was really something that had never been seen by these people before. For example, the Rocky Mountain gold diggers woke up in the middle of the night because the aurora were so bright that they could read in the auroral light. And then can you go forward? Yes, here are the auroral sightings which have been seen on Earth. I mean, historical records are showing where on Earth people see aurora, and you can see that these auroral sightings go to very, very low latitudes, to Caribbean on the American sector, and then to South China in the Chinese sector. Then let's go forward. Oh, sorry. Can you go back one? I draw the spot here, a black spot, to mark the Mumbai city of Mumbai. And let's go forward then. Here is the city of Mumbai actually had a magnetometer in that time, which was a very good thing, because we can look at some of those impacts in Mumbai. We also had a magnetometer here in Finland, which was recording at the time, but that space weather event was so large that the magnetometer it went off the scale of the magnetometer. But here you can see this disturbance which was observed in Mumbai during the Carrington storm. And this disturbance is the same size magnitude which tripped the Swedish power grid in Malmö in 2003 during a much smaller solar storm. Then let's go forward. Thank you. Here you can see recurrence likelihood. There's a kind of a thumb rule, even though the sun doesn't obey any rules. These happen once in 100 or 150 years, or twice in a year, because now this is a statistical likelihood. Sun could launch 2 of these in a week and then wait for 300 years, and the statistical likelihood would still be once in 150 years. Chapman et al. Says that it's about a 1% annual recurrence risk, the same as for pandemics. And here you can see a background picture from the sun in October 2014, and this big spot which you can see on the middle is the same size as the Carrington spot. If you push the one more time, yes, thank you. I draw the Carrington spot in scale here, but this didn't erupt, this spot. In 2012, however, NASA's stereo satellite observed a Carrington scale eruption, which bypassed the Earth by a couple of days. And we know that it was a Carrington scale eruption because NASA's stereo measured that strength of the magnetic field of that eruption. And we know in scientific community that this will occur. It's a question of when. Then can we go forward? Thank you. Here is a measure of solar activity, which is called a number of sunspots. This is has been already recorded by Galileo Galilei from 1600s onwards. And when there's a lot of sunspots on the sun, the sun is very active, and then it sends lots of eruptions towards this way. And here you can see this famous 11-year cycle. So in every 11 years, the sunspot number is in maximum. So sun is very magnetically active, and then every 11 years it's less active. And then if you can push 3 times, I think, and then one more time, here you can see those large storms. 1770 was a large storm, and we know this because also during this time there was historical recordings of aurora in the very low latitudes. And here we know that, okay, if there's recordings of aurora in low latitudes, auroral zone has extended towards the equator. Carrington was 1859. 1921 there was one storm which was almost as large as the Carrington, but not as large. And then we can see the near miss here in 2012, and then we can push, I think, twice. Yes, and now we don't know how large the current cycle is and when the next one comes, but what we know is that this has occurred so regularly during the history that it will occur. It's just a question of when. And let's go forward then. Thank you. And here I'm now going to the Research Council of Finland project results, and let's go forward. Here the results are in short. First of all, we modeled the Carrington storm in the Finnish power grid, and we think that the Finnish power grid will most likely endure. The estimate of the geoelectric field was about 10 millivolts per meter, or a little bit more. And why is this? Is because we have a transformer technology which is kind of enduring well these extra DC currents. Then we have a long-term preparedness for this event. We've had already first investigations for this type of events already from the 1970s onward. And then actually one of the largest results or reasons is that the largest currents will move southward from Finland. And actually it is the Central European and lower latitudes which will be feeling the larger ionospheric currents and therefore also the larger geomagnetically induced currents. Then from the satellites, we divided into two types, kind of the big ESA satellites, which have been very well built and tested, and for example, Galileo and Copernicus. These satellites will go to safe mode during this kind of a storm, and due to the bit flips, due to the solar particles, and we don't know whether these satellites will recover. However, the new space fleet, for example, Elon Musk's Starlink satellites, will most likely be entirely lost due to the radiation exposure and bit flips. And we think the recovery of these satellites will be unlikely. And one of the important things is that during this kind of a storm, satellite signals will be lost because the satellites are either lost or in the safe mode. And the recovery of those signals depends whether those satellites recover. And of course, there are dependent services, navigation, and some mobile networks and so on, aviation. And then let's go forward. Here I just very briefly just mentioned that these signals in the polar cap, if we can push once or twice, I think. Here on red is the area which will be affected by those signals, and on background you can see world's flight routes. And you can see that most of those flight routes are actually on the affected area, and here on the right you can see the dose levels on the flight altitudes. And if we push once, I think, yes. So I think, I mean, one of those things is that if we rely on kind of getting somebody from overseas to help in these kinds of situations, this might be problematic because the flights are probably rerouted during this kind of a storm. And then the last slide, I think this is the summary slide. So in summary, Carrington Storm is about 3 to 5 times larger than anything that has been observed during the space age, and the impacts will be global power supply, and the longer the transmission line is, the larger are the DC currents. And then the satellites and systems using satellite signals like time synchronization will also be disturbed. And effects may be surprising for those technologies that prepare for more of the same. And if your system depends on Carrington sensitive technology, what we have done here in Finland is that we have investigated, tested, and monitored this thing continuously from the 70s onwards. And there is an easy and cost-effective mitigation measure which can be applied, and this is the preparedness protocols from which Risto has talked many times. And I would also like to say that we are already on long time, and the next Carrington can come basically tomorrow or thrice in the next 100 years. Thank you so much for giving me this opportunity to talk to you. I believe we have a question and answer section after Antti's talk.
Right. So I'm sure there will be a lot of questions coming towards you. And that was a great presentation, Professor Pamral. And so you made everybody realize, so there are a lot of experts in here also, made everybody realize that how important this event is. A lot of information we also have gathered from your presentation. So next I would invite Professor Pulkkinen, if you can share your presentation, or if you want, we can make you the co-host.
Let's try. I'm going to try to share first.
Shonendu, can you make Professor the co-host so that he can share?
Do you see my slides?
Yes, it's visible.
Okay. Are we good to go?
Absolutely, sir. You can start.
All right. Well, thank you very much. And thank you for the invitation to present to this group. It's honor and pleasure to have this discussion. As Risto mentioned, I am the director for Heliophysics Science Division at NASA Goddard Space Flight Center. Goddard, as also Risto indicated, is the NASA's largest science center. We have all key four NASA science areas represented at Goddard Space Flight Center: Earth Science, Astrophysics, Planetary Sciences, and Heliophysics. And I'm in charge of leading the heliophysics side of things at Goddard, and we are the largest concentration of heliophysicists on the planet, doing theory modeling, instrument development, mission development, and so forth. So my day-to-day job is really to push the organization forward, but today I'll be wearing my researcher hat. Over the past couple plus decades, one of my pet scientific research areas have been around geomagnetically induced currents, or GICs, that you have heard about. So what I will do in my brief notes here is to just describe some of my experiences in this work over the past couple of decades, especially focusing a little bit on the impact side of things. I mean, I've already elaborated a little bit on the GIC side of things and what the impacts could look like. I'll kind of dive a little bit deeper to that topic. And the primary focus, I would say, for this presentation is to discuss the US GIC, or geomagnetic disturbance standards. As Risto also indicated, US now has a regulatory framework in place that requires all the US utilities that operate systems above 200 kilovolts to have response plans in place, and also to have carried out hazard assessment. So I'll talk about that work and what that regulatory framework looks like on the US side, and maybe that will give some ideas how others might use that information and lessons learned for their work as well. So that's the plan here. But before going into the kind of impact discussion, just a very brief history of the high-level United States interest in the topic of space weather, and in particular the topic of geomagnetically induced currents and the impact on the high-voltage power transmission systems. Really, a lot of the high-level, and with the high-level I mean federal government level discussions, and as you will see here, these discussions have penetrated all the way to the White House level. I would say that a lot of these discussions were initiated by the National Academy's workshop that took place here in Washington, D.C. 2008. I was fortunate enough to be able to attend that workshop myself. And the workshop was titled Severe Space Weather Events, Understanding Societal and Economic Impacts. And this was really interesting workshop because it had participants from different corners of the federal government. And there were also a few scientists that gave very appealing presentations about what these Carrington scale storms can look like, what once in a 100-year frequency storms could look like from the viewpoint of the GICs, the geomagnetically induced currents, and the impact on the US high voltage power transmission systems. And that piece combined with the presentations from Department of Homeland Security, US Department of Homeland Security, where the DHS folks indicated how intimately we are dependent on the reliable transmission of power. Virtually all corners of our modern existence are one way or another dependent on the reliable transmission of electricity. So that really sent a very strong message. The Carrington storm scenario combined with the dependence on that transmission of electric power created, really, kind of a substantial awakening moment, if you will, on the federal government participants in that very workshop. And that really sort of kicked into motion several threads of actions at the federal government level. One was this joint work by US Department of Energy and North American Electric Reliability Corporation, or NERC, which is sort of a quasi-regulatory body here in the North America and the United States. The Department of Energy and North American Electric Reliability Corporation published this influential document. And, by the way, all the documents that I'm going to show here are available publicly, so you can go and dive into the details at your pleasure. The report was titled High Impact Low Frequency Event Risk to the North American Bulk Power System. And the report really echoed a lot of the findings from that earlier National Academies workshop from 2008, indicating that, in case of this Carrington scale storms, there may be a very substantial and long-lasting impact on the North American high voltage power transmission infrastructure. Then there was another, again, a little bit more detailed study, this time carried again by the North American Electric Reliability Corporation, or NERC, and this was titled Effects of Geomagnetic Disturbances on the Bulk Power System. And this was released February 2012. Again, echoing a lot of the findings from these earlier reports. There was an interesting shift, though, here in the kind of the focus on the impact side of things. We'll talk about the impacts in a couple of slides here. The earlier studies indicated that the thermal impact related to the extreme space weather storms is the primary concern, and of course the thermal impact could lead to a permanent damage to the high voltage power transmission systems, and that was really the end of the world scenario, if you will. If you have hundreds of high voltage power transmissions, transformers permanently damaged, that means that you are looking at long-lasting electrical blackouts in major regions across the United States. However, this February 2012 report shifted the focus to a voltage collapse. So the report found that because of the nature of the signal of the geomagnetically induced currents, it looks like maybe the thermal impact is not the primary concern, but it's really the voltage stability that is the primary concern, and the voltage collapse associated with these extreme storms, such as Carrington scale storms, that is the primary concern. And that thinking still is the kind of the thinking, at least here on the US side of things. Based on all of that, federal government acknowledged that something needs to be done at the regulatory level, and Federal Energy Regulatory Commission issued an order number 779, which is the title page from that order on this slide, and that really changed the game. So the Federal Energy Regulatory Commission directed NERC to develop geomagnetic disturbance or space weather standards. And I was fortunate enough to be member of the standards drafting team. I wouldn't say, Rista, I appreciate your comment that I'm the father of the regulations here in the US, but I really was just a member of the standards drafting team and providing sort of that scientific research input to the drafting team deliberations, including providing kind of a scientific information about what these Carrington events could look like from the bulk power transmission system standpoint. The FERC, and I'll talk more about the FERC and NERC work in a couple slides here. There were two threads to this. One is the emergency operations planning piece of the regulatory framework, and then also the hazard assessments part of the framework that now are in the books, and U.S. utilities need to be compliant. Another thread to the work here in the U.S. and then kind of a high-level U.S. federal government attention to space weather came through new national space weather strategy that was developed at the National Science and Technology Council level. The first version of the National Space Weather Strategy came out October 2015. And of course, the National Space Weather Science and Technology Council is a branch of the White House. So at that point, we had a White House level attention to the topic, and White House level acknowledgement from the Obama administration that something needs to be done at the federal government level. The National Space Weather Strategy addresses all the different areas of the space weather impacts that Minna was talking about, including the GPS distortions, high-frequency radio communication disruptions, impact on the spacecraft, and what have you. But I would say that there's still the core focus around the National Space Weather Strategy was still on the bulk power system and the concern about the impact of a Carrington scale storm on the U.S. high voltage power transmission system. Then there have been several versions of the National Space Weather Strategy that were that came out from the different administrations. The next version of this came from out from the Trump administration, and during the Trump administration, the National Space Weather Action Plan and Strategy and Action Plan was actually codified into a federal law. So there was a congressional bill that was passed, and it's called the Pro-SWIFT Act. And the Pro-SWIFT Act really codifies the National Space Weather Strategy into a congressional law. So it's really law of the land right now in that sense. And the very latest incarnation of the action plan and the National Space Weather Strategy came from the Biden administration just late last year. It was released in December 2023. So you can see the arc here, and how the kind of attention from the U.S. Federal government has been evolving over the past 10 plus years, and we have now reached all the way to the kind of a top tier, if you will, of the federal government, and having attention also from the White House level through the National Space Weather Strategy. Okay, so let's talk a little bit more of the impacts over the next couple slides. So this is a graphical illustration of the same story that Minna told, with using a little bit more kind of a graphical approach. And what this cartoon shows there is kind of the top piece of the cartoon shows this loop structure. That loop structure is kind of a capture of the electric current systems in the near space, in the ionosphere, in the magnetosphere, and even in the kind of interplanetary medium in the solar wind. So during major space storms, as Minna was indicating, we have these very large electric current systems of the order of million amperes that will experience very large spatial and temporal variations. And those spatial temporal variations will induce secondary electric currents in the surrounding conducting bodies. And the conducting body, of course, in our case here, and in the case of our interest, is the surface of the Earth. So these spatial temporally changing electric current systems, major electric current systems in the near space, induce an electric field on the surface of the Earth. And of course, as Minna indicated, the nature and the magnitude of that electric field is very intimately dependent on the local ground conductivity structures. And then the geoelectric field, this is an electric field that we call a geoelectric field, again indicated by Minna. And this geoelectric field can drive electric currents in long conductor systems on the surface of the Earth. Long conductor systems can be buried pipelines, railway systems, but the main concern pertains to the high voltage power transmission systems, where this geoelectric field drives these electric currents that we call geomagnetically induced currents, or GIC. And simply speaking, the amplitude of the GIC is related to the line integral of that geoelectric field across the terminals of the systems. So the longer you have, longer systems you have, and higher, the lower the resistance, the higher the induced currents will be, and potentially higher the impact on the system performance will be as well. And as Minna indicated, really the kind of the most significant threat is around the auroral region that typically extends kind of at the northern latitudes during normal conditions during the Carrington Storms. Scales, as Minna indicated, the auroral current systems can penetrate to very low latitudes. But even without Carrington scale storms, you can have large induced geoelectric fields that can be introduced at the mid latitudes or even at the equatorial latitudes. A lot of that depends again on the local ground conductivity structures. If you are in areas where you have poor ground conductivity, you can set up fairly sizable geoelectric fields, even during storms that are smaller than the Carrington scale. So it is true to state that the GICs and the GIC related problems can be a global phenomenon and global challenge. In terms of the impact on the high voltage power transmission system, really the primary means for these induced currents to impact on the system performance is through half cycle saturation. And then we have a lot of power engineers here, so you understand what that half cycle saturation means. I don't claim to be a power engineer, but this is something that I have learned through my communications with the power engineers themselves. And it's the half cycle saturation when these quasi-DC induced current flows through the system that we have an introduction of kind of a series of secondary impacts. One is that when you have a saturated power transformer, the saturation causes leakage of the flux from the core of the transformer, and that leaked magnetic field, AC magnetic field, can create eddies in parts of the transformer where you do not want to have these extra eddies, and that can lead to a transformer heating, and even in worst cases to permanent heating related damage to some of the key components of the transformer. Here's on the left hand side, it's an image, the famous image from March 1989, and this is one of the transformers in New Jersey in the United States that got permanently damaged because of this kind of a mechanism through the leakage of the magnetic field. The second impact is that the saturated transformers distort the waveform that you're pushing through the system. And of course, that distorted waveform is another term for it is that you will have harmonics in the system. And as you all, of course, know, you have a lot of sensors sniffing the harmonics in the system. And if those harmonics get past certain threshold levels, the sensors can actually trip some of the systems offline. And that is, for example, what happened in Malmö, southern Sweden, during the October 2003 storm. There was a regional blackout during a major phase of the storm, and the relay tripping was the primary mechanism that created the blackout in that region during that storm. And then the final key impact is that you will have fluctuations in the reactive power. And of course, this is, you will have the changes in the phase angle between the current and the voltage in the system. And of course, that angle is intimately related to the voltage of the system. And in worst cases, if you have, these too large fluctuations, you can have, instabilities in the voltage. And in worst cases, you can have a voltage collapse, which will be leading, of course, to electrical blackout. And it turns out that actually the harmonics and the voltage instability were the primary mechanisms that brought down the hydro-CAPEX system during March 1989. So this is the most famous electrical blackout caused by space weather storms. There was a several-hour lasting electrical blackout that left millions of people out of power for several hours during this famous March 1989 storm. And as we have gone back and looked at the primary mechanisms, it turns out that it was really the harmonics that tripped some of the key lines out of service, and related voltage instabilities and fluctuations ultimately created a voltage collapse that took out the entire system. So again, going back to my discussion about the primary impact, I would say that the first there in the top, the leakage magnetic fields and transformer heating, was initially thought here in the US as the primary mechanism for major impact on the bulk power system. But now the thinking has transitioned a little bit, and now the thinking is that it's probably the harmonic currents, the harmonic currents in the system, and the voltage fluctuations and voltage instabilities that are the primary concern from the system performance standpoint. Okay, so let's then have spent a few minutes here talking about the US geomagnetic or GMD standards. Again, the key piece that changed the game here in the US was the order from Federal Energy Regulatory Commission, the order number 779 that came out May 2013. And in this order, FERC ordered North American Electric Reliability Corporation to develop geomagnetic disturbance, or GMD, standards. I was again fortunate enough to be the kind of the scientific member in this standard drafting team that worked over actually in several years and made several revisions to the standards in the process. But from the kind of a top level, the FERC order indicated that there needs to be 2 levels of the standards, and the first standard that we have now in the books is the called Emergency Operations Standard EOP-010-1, and this is a kind of a regulatory framework that requires that all US utilities that operate at 200 kilovolts or above need to have a plan in place in their operating rooms in case of major geomagnetic disturbances, in case of major space weather storms. So you can see, if you can read the R1 there toward the bottom of the standard, it states, this is a requirement 1, it states that each reliability coordinator shall develop, maintain, and implement a GMD operating plan. So that's the core piece. So all US utilities need to have a folder somewhere in the operating room that states the A to Z, what are you going to do if there is a major GMD event? And of course, the operators need to be trained so that they understand what those A to Zs are and what GMDs can do to their systems. The second piece to this is the TPL-007, and this is the transmission planning related standard part of the GMD related regulatory framework. And in this part of the standard, the US utilities, again, all utilities operating at 200 kV or above have to carry out hazard assessments. And as a part of this, we worked really hard with the scientific community here in the US to create these so-called benchmark geomagnetic disturbance events. Kind of loosely speaking, you could say that we created what the Carrington scale storm could look like. Really, the quantification here everywhere in the standard is the once in 100-year storm. So we did a lot of statistical assessments of the observational data sets and characterized what that geoelectric field could look like in a once in 100-year storm setting. Again, loosely speaking, Carrington scale storm setting. And so all the utilities need to take this benchmark geomagnetic disturbance event, once in 100-year storm event, and drive that scenario through their systems, do the assessments of the voltage stability, the reactive power sort of fluctuations in the system, analyze the harmonics that get pushed through the system, and also do a thermal assessment, thermal impacts assessments. Okay, and right now we're sort of in the finishing end of the TPL-007. So I believe it's by the end of this calendar year, all the utilities need to have documentation showing that they have carried out these assessments and carried out also the developed corrective action plans if their analysis indicates that they do not pass certain thresholds or certain criteria. So again, these are the 2 key pieces right now in the books. The FERC order indicated that we need to have 2 sets of regulations or standards in place. One pertaining to the operating plans. What do you do in case of a major space weather event, in case of major geomagnetic disturbance or major geomagnetically induced current event? And then the second piece being the transmission planning, where all the utilities need to drive through these storm scenarios, drive through these benchmark events through their systems and analyze and model what the impact will be. And of course, these benchmark events, and again, all this information is publicly available. We know that many of our partners and colleagues around the globe have used these benchmarks that were developed in the NERC work and see what it means for their location. The benchmark event that we developed in this contest can be applied anywhere on the planet. All you essentially need to know is the location of interest, and the benchmark can be tailored for that location of interest. So that could be a good start for for initial assessments at very least. So just a kind of a couple concluding remarks here. GIC, the geomagnetically induced currents, can impact power systems globally. Often people think that this is only high latitude problem, but no, we know that you can have impacts also at the mid and low latitudes, especially during these major and extreme events such as Carrington scale events. And it also appears now, at least in the assessments that we have down here in the United States, that states that the voltage instability and the harmonics are the most significant challenge in operating the bulk power transmission systems through these extreme space weather storms. The second bullet, I would say that yes, from the regulatory framework standpoint, the U.S. is right now the best prepared nation because all the U.S. utilities are required to have carried out hazard assessments, and they have also these storm operating plans in place in their operating rooms. And then the final point is that the work is not done, right? We are creating new scientific understanding about these extremes, and all that new understanding will allow us to refine what these extreme benchmarks can look like, and what the kind of storm scenarios in once in 100-year settings or Carrington scale settings can look like. And that new scientific understanding and information then can be fed to a corresponding impact assessments as we revise also the hazard assessments over time. And I will stop there. Thank you.
Professor, thank you so much for your wonderful presentation. So I think now we can move on to our session where we can have a discussion, and I would like to invite experts and professionals from the Power Grid India and the power pools of East, West, and South Africa. They can share their views on the discussions today, after which we can move on to the question and answer session. So is there anybody from Power Grid India who would like to discuss with the experts? You can have your questions also. Already I started receiving several questions from the experts. So we'll take that in the question answer session. So is there anybody from the power pools?
Yeah, hello. This is Ram Kumar from Grid India. In one of the slides, Amina has told that the DC currents would be the impact on the impact of DC currents would be higher for the longer lines. So I just wanted to understand how and why the reasons behind it.
Yes, thank you. Excellent question. So it is like to do with the how long conductor you have on the electric field. So the longer travel time for the conductor within the electric field, the longer is the electric potential, and therefore also the DC current on that conductor. So if the conductor is grounded every 50 centimeters, then the current which is on that conductor are smaller. So if you have like grounding which is thousands of kilometers or at least hundreds of kilometers, then the currents on those conductors will be larger.
Thank you.
Do we have anyone else from Power Grid India or the African power pools? We'll wait for them sometime. We'll wait for 1 minute. Yes, Mr. Naveen Kumar, you may put your question.
I'm Naveen Kumar, Assistant Director from Central Electricity Authority. I just wanted to know, is there any mitigation infrastructure possible which are like more cost economic? Because upgrading, making the grid more hard against these solar flares, coronal mass ejaculations. Is there any more viable cost economic option available in this to tackle all these problems?
Yeah, no, again, that's a really good question, of course. You could say that there are two layers of mitigation options. One is to harden the grid in first place, kind of engineer your way around it. But as you indicated there, it can be very costly. In the US, some of the utilities have taken kind of at least partially that route. One of the things that you can do is that many of the transformer, high voltage power transformer manufacturers now have GIC with stand designs as a part of the new designs. So some of the new high voltage power transformers are able to tolerate higher amplitude GICs flowing through the system and not creating these kind of secondary impacts at the same level as, for example, some of the older auto transformers. Another measure to harden the grid is to install DC blockers in the grounding neutrals. So there are designs and there are entities that are capable of manufacturing these DC blockers that you can put in the neutrals, and of course that blocks the GIC flow in that segment of the line. So if you have a knowledge about some especially vulnerable location of transformer in the system, you may want to consider kind of having these blockers in that specific location. But I would say that the most common mitigation option that the US utilities are exercising are the operational mitigation actions. So not necessarily taking any kind of hardware approach or hardware actions, but they have the plan, what switching I'm going to do in the system, how do I inject a reserve power in the system if I start to see voltage fluctuations and so forth. So they have an operational plan how to kind of work their way around the storm and weather the storm, if you will. So I think there are a lot of lessons learned from the US utilities, how you can address this problem from the operational plan viewpoint.
Yeah, if I may just add here, this is exactly the same in Finland. So in Finland is a smaller country, of course, than the US, and we only have a one grid company. So we don't basically kind of need a law against this, because we can just ensure that our grid company is aware of this, and this is what they are. And exactly these plans, which Antti said, they are the most cost efficient because they don't cost anything. That if you know what you are doing, it's already a great thing.
Okay, thank you very much for answering this question. I just want to know one more little thing. As you know, there is more renewable energy incorporation in grid. And has there been any study which is relating this phenomena to solar farms? Like we have a lot of solar farms, how they are impacted, what is the more precaution of this in solar farms? Like what will be the things which we are going to face because there will be a solar farms? Is there any more serious issue? Like we know there is GIC, which is like probleming the power transformer harmonics and heating issue, and then leads to blackout. But is there anything which is signifying that it may affect solar farms in other ways, or there may be some other reasons, or more to explore? Can you just put a light on that?
Yeah, I mean, I will again say, and this is a really timely question. There was a IEEE conference here in the DC just a few weeks back, and I was one of the panelists there. And while many of the participants acknowledged that the standards have helped them to understand what the exposure to this space with the phenomenon is, there was also acknowledgement that the technology is evolving. Renewables are the new way of life, solar power, wind power, and you also use more precise GPS timing to operate some pieces of the system. And I think that piece is still at least in the US, something that needs to be studied. So I don't think we have a good understanding what the evolution of the bulk power system in general means, also from the exposure to the space with a hazard standpoint. So I would say that the regulatory framework that we have in the US in place is something. It was a snapshot to the technology that we had in place a few years back, and I think there needs to be a revision of these assessments that really takes into account these new technologies that we have in place right now.
Yes, and if I may, I could add into here. Basically, the bottom line from the perspective of the geomagnetically induced currents is the amount of the amplitude of the geoelectric field and how vulnerable your dedicated system is to that electric field. And if basically your solar panels or whatever devices you have, if they can endure 10 millivolts per meter or larger locally, then they should be okay. So basically this magnetically induced currents are basically a problem for longer transmission lines. But exactly as Antti said, after our project ended, where we were looking at the impact on the critical infrastructure in Finland, one of the major things that really woke up our National Emergency Supply Agency, which is in charge of Finnish preparedness, basically like electricity and so forth, import, export, and so forth. What they really understood after our project is that this is a holistic whole. Everything affects everything. If we, for example, lose communication networks, and what is that then doing to your local devices? If we lose navigation signals, what does that do to your system? If we can't communicate as or share data, it will be difficult to. This is one thing that needs to be taken into account, and it's not only an engineering problem, it's also a preparedness community problem. Thank you.
Thank you.
Thank you so much. Thank you.
We have a question from Mr. Ram Kumar. If you can put forward your question.
Yes, my question is regarding a Vulcan slide where it was mentioning that there would be an increased reactive power consumption during these events. But from the whole webinar, I understand the issue is with respect to DC currents. So I'm confused how the DC currents and reactive power are not related. So can you throw some more light on how the reactive power issues would pop up in the grid?
Yeah, it's really through the primary mechanism how the DC current can impact the system performance is that it creates this additional flux component in the high voltage power transformers, and that additional flux that is being pushed through the core of the transformer pushes it to the saturated state, because it's a DC current, it's kind of the half portion of that saturation curve is on the saturated portion of the system, and it's really that half cycle saturation of the system that then leads to these secondary impacts, the harmonics in the system, the leakage of the flux from the core of the transformer, and also to the change in the phase angle between the current and the voltage in the system that can then lead to the reactive power fluctuations. So really, it's the half cycle saturation that is the primary impact that you have on the system. Then you have this kind of a secondary effects through that, if you will.
Yeah, thank you very much.
I have a question. So one thing is that, as you have mentioned, that transformers or our power grid can have voltage or harmonic instabilities. There can be harmonics induced and voltage instabilities can be there. But what about the satellites? Because if there is some mitigation things that can be done for the transformers and the power grids, what can we do for satellites? Because this is an important part. Because once we lose communication, then a lot of important things are lost, right? So how can we mitigate that?
Absolutely, this is a fantastic question, and exactly our emergency supply agency here in Finland was kind of more aware of the geomagnetically induced currents, but really the news from our projects was kind of coming from the satellite part. And I mean, basically, it's a question mark how the satellites will endure these storms. We know that some of those satellites which have been built very fast and launched very fast, basically these satellites which are commercial satellites, for example, the Starlinks and so on, we are pretty sure that they will be lost entirely during this kind of a Carrington storm. Of course, we cannot be entirely certain about this, but this is what our guess, that they will be lost. But however, there are many of these commercial satellite companies, for example, Starlinks and so on, they have this system anyway to launch often. So their mitigation would then probably be to just launch new satellites. However, of course, I mean, if they lose like 10,000 satellites at the same time, maybe it has to do with their business model or something. I'm probably some satellite companies will go to bankrupt or something like that. Then this is like the fast built satellites, those which do not care about radiation so much, because these satellite companies are launching to lower altitudes, to what we call LEO, low Earth orbit, about 500 kilometer or altitudes. They don't have to care in normal circumstances about the radiation, but during this Carrington scale storm, these radiation belts, which I showed to you, they will come closer to the Earth. So basically, also those altitudes where those satellites are will be exposed to radiation, and therefore, if they are not considering radiation at all, they will be affected. This has to do with those commercial companies. Then we have organization satellites like ESA satellites, NASA satellites, the Galileo, the GPS, the GLONASS, these navigation satellites. They are typically well built. It takes several years for them to build these. They use radiation hard components. They have much of those automatics in the satellite, which kind of detect the environment in space and then can go automatically to safe mode. And we were talking during this project, we were talking to these people who are in charge of the ESA satellites, and they said that they think that these conditions will take their satellites to safe mode. So basically, in a safe mode, a satellite doesn't send signals at all. It just listens to commands from ground. So all in all, the satellite business is like either you lose your satellite or your satellite signals aren't available. And this is of course a problem. For example, many mobile networks don't use atomic clocks anymore, but they take the time synchronization signal from the satellite. And if that satellite is not providing that signal, of course, it's a problem for the mobile network. So it's also, it's a combination of different problems. I mean, for example, it can happen that there's a blackout, for example, in some country, and then the mobile network is at the same time out of order. And therefore, it's kind of adding difficulty in handling these situations. But as Antti said, I want to stress here and emphasize that this satellite business is really an open question. This is our best guess at this point are the ones which I told you earlier, but the really new investigations and new research is needed to really understand this, how this, what this does to our satellites. And especially now when there are more and more satellites coming every year, like thousands of satellites will be launched. So the satellite business is, in my opinion, something that hasn't been looked at too much in the past and should be in more focus in the future. Thank you.
Yeah, I mean, and if I may, just from the NASA standpoint, as Minna indicated, of course, we are very aware of the hazards, and radiation hardening and radiation analysis is one of the required pieces of any satellite design or spacecraft design that we have. Some are better hardened than the others. For example, in heliophysics, our spacecraft tend to be very well radiation hardened because we are there to observe the radiation conditions. So, for example, the July 2012 event that Minna mentioned, which was the major space weather event that just missed the Earth, the stereo spacecraft that was on the path of that storm, because of the design of the spacecraft, we not only survived, but we were able to observe what that storm looked like from that in situ conditions. So I would say that from the agency, from NASA perspective, it's really kind of the radiation hardening piece, and the fact that there is a requirement in our project life cycle to have these considerations taken into account, that makes us fairly well prepared. Of course, if you have once in 100-year storm Carrington scale, there's still a lot of open questions. But I would say that, like Minna pointed out, it's really the kind of the new space business and the new commercial entities out there that might not be quite as well aware of the space weather effects that are the primary concern here.
Okay. Thank you, professors, again. So as we are running quite late, I would request all the participants who have questions, they can kindly post it into the chat box. Also, we do have a feedback form. You can post your questions there, and if professors agree, we can send them the questions. If the professors have free time, they can answer these questions, and we can post these questions again to our website. We'll send the link. And now we are reaching conclusion of this webinar. So, and Dr. Ajay Mathur is also here. So I welcome Dr. Ajay Mathur to deliver the vote of thanks. He is the Director General of the International Solar Alliance. And Dr. Mathur has been pivotal in fostering global solar growth. His illustrious career includes leading roles at TERI, contributions to the Prime Minister of India's Council on Climate Change, and key positions in global energy initiatives. Dr. Mathur's work in energy efficiency and climate negotiations has been widely recognized. He is a recipient of many distinguished awards for his environmental and energy-related efforts. Dr. Mathur's expertise and leadership in climate change and energy efficiency are truly inspiring. Welcome, sir, and over to you, sir, for the vote of thanks.
Thank you very much, Richik. I was a little embarrassed by the very generous introduction that you provided. But I must say, this has also been a huge learning experience. I particularly want to thank Minna Palmroth and Antti Pulkkinen for their wonderful presentations. Narasimhan, thank you very much for making this happen. I'm also very grateful to Dr. Gon Chaudhary for enabling this presentation. I think it was Dr. Gon Chaudhary who first brought Carrington Storms to our attention. I would propose that after hearing the presentations today, we discuss two approaches to move ahead. They're not either or, but and. The first approach is about grids. Now, it's fairly clear with the thousands of renewable energy projects that will be set up. So somebody was saying that within the next 5 years or so, we will see about 3,000 more gigawatts of solar capacity come up. This would imply that the 80,000 kilometers of, 80 million kilometers, not 1,000, 80 million kilometers of transmission lines would require another 80 million kilometers of transmission lines. Now, this is huge. I think, number one, we need to reach out to grid operators across the world. Auntie presented a number of things which could be done. For example, every grid could be required to see how the readiness for performance of the grid during a solar storm. I think it makes sense for us to carry this through. And I think Mr. Soni had put something in the chat box about Geo15 focused discussion on this area. This is something that I think we should take up. And Dr. Jogan Chaudhary, Mr. Soni, Mr. Narasimhan, Meena, Auntie, I think this is something that we would be very happy to push ahead as well. And I think the work that has already been done, particularly the Finnish work and the US government work, would help provide the background for that. The second thing that I think is important is, as the question I think was asked, I think it was by Naveen, if I'm not wrong, about the impact of solar farms in particular on this. As the International Solar Alliance, that's something that we are concerned about. Would the design of solar plants change? Are there scale effects? If they're bigger than something? Yes, obviously there's a grid factor. And normally what would happen is that because of land availability, the solar plants will be built typically far from where the load centers are, so the lines will be long. So that's one part. But the second part is that the solar farms themselves could possibly lead to. Now, this is something on which, as a Solar Alliance, we would be very happy to work with the Finnish Met organization or with the Goddard Space Center on issues related to how we study this, how do we assess this, and if changes need to be made to the standards for new solar plants, how do we do it? I think it is very clear that a long overdue Carrington storm, as was mentioned by Meena, I was completely taken aback by the numbers that it could happen now, or you could have to be in the next 100 years. This is frightening because, amongst other things, what it tells us is the huge vulnerabilities that we have. What I think we need to focus on is, number one, creating an awareness that these kinds of protections are needed, protections to Carrington Storms, especially as far as grids is concerned, and I don't know where the work on solar farms will lead us. Second, as grid operators, what are the mandatory things that grid operators should do, and what are the preferential things that they should do? I think it would help greatly. Now, it is quite possible, I am not a grid expert, but I have no idea whether the grid organizations like SIGRE have got standards on this or not. But if not, then we can certainly help in raising the awareness for carrying this out. I also noted, Auntie, that much of the work in the US was started out by a academies workshop. And that is something else, Mr. Soni, both you and I are members of the National Academy of Engineering, that we could help steer a discussion on this subject as we move ahead. Finally, to all of you, many, many thanks, both for attending this webinar as well as for the stimulating discussion that it has generated. More than anything else, Meena and Auntie, I'm very grateful to you for making us think. Thank you very, very much.
Thank you.
Thank you very much. The pleasure was on our side.
Thank you,
Thank you.
Dr.
Thank you.
Thank you very much.
Thank you. Bye-bye.
Such a pleasure.
Thank you.
Thank you so much.
Bye.
I think we can close the webinar now. We have posted the webinar link form, and participants, I'm very sorry we don't have time, but you can post your questions in the feedback form and also in the chat box. I will send them to the speakers. And Professor Gaun Chaudhary sir, if you can say a few words, and then I will close. That would be great.
No, it's all right. Thank you very much. Thank you all for joining this wonderful webinar. Thank you, everyone. Thank you, the speakers. Thank you, everyone. Thank you.
Thank you.
Thank you, sir. Thank you, sir.